Due to certain private reasons, so the next talk will be cancelled. So we will move on to the next speaker from the Professor Zhongzhu Yang from Central University. Today he will talk about the investigation of the magnetic behavior of the spinel material by using a neutron technique.
Okay, test. Okay, sounds good. Okay. Good afternoon. My name is Zhongzhu Yang. I come from the Department of Physics, National Central University. So in the beginning, I want to thank the invitation from Yangu. So they give me an opportunity to present my recently research work. So my research work is investigation of the complex magnetic behavior of spinel material Fe3B308. And maybe you are curious that why does this chemical formula is spinel structure? Because if you divide the number by 2, you will get the ion 1.5, V 1.5, and O4, which is very close to the 124 or 214 spinel structure. So this is a very complex system, so I want to spend some time for some introduction. So this is my outline. So in the beginning, I will focus on, there are 3 very important papers in this field, and give you a more detail in the introduction. And then I will go to the sample characterization. So I want to thank first for the NSRC for supporting not only the granted bin time, but also the traveling expenses. Okay. And then I will talk about some thermal properties. We measure some specific heat, and we also have measured the magnetic property, including the magnetic susceptibility, hysteresis loop, and we also do some neutron magnetic scattering. And finally, I will just talk about my very recent result that I just go to the ENSTO last month. So we collect the latest inelastic neutron scattering data. So because this is an ongoing research, so maybe I can give you a final result for you, but I will talk about some progress currently, and I will give you a conclusion in the end. Okay, so in the beginning, I was talking about the crystal structure of the spinel. Because the crystal structure is very important in this study, and typically this is a simplified picture of the spinel structure. We can if this is the unit cell of spinel, we can divide it by 8. So there are two types of sub-lattice. We will call there will be an A side and a B side. And at each side, there is a cation ion. And in the A side, typically we have a divalent ion, and the B side is a trivalent ion. And if the A side with the divalent ion and B side is trivalent ion, we will call it normal spinel. And if we put the trivalent in the A side and the divalent in the B side, we will call the inverse spinel. And in the A side, you can see it was surrounded by the 4 oxygen ions. Actually, we made in another symbol we call X. So there are 4 X ions. In my case, is oxygen. Okay. And the B side was if the cation ion was surrounded by another 6 oxygen ions. So A side will be formed as a pyramid, and the B side will form as a octahedron. Okay, this is a typical spinel structure. But in this system, it is very originally it would be very simple, because if you use the Mg and the Al in the A side and the B side, that's what we call the standard or the typical spinel structure. But once you put the transition metal into the A side and B side, the things become very different. Because, for example, if you put the ion, divariant ion 2 plus in the A side and the vanadium 3 plus in the B side, you would need to take consider about its electron configuration. For example, the divariant ion have electron configuration 3d6, which means we fill the 6 electrons into 5 3d orbitals. And one more electron will be filled in the EG orbital with anti-parallel spin orientation. So only 3d orbitals are at least half field. And for the vanadium, if this is 3 plus, that they have electron configuration of 3d2. That means we have 2 electrons that fill into the T2G orbital, and there are 3 degree of freedom. 3 unoccupied orbital here. And in this case, the ion will be formed at 4 mu b. We know that the magnetic moment will be the Gz mu b. And in this case, with orbital quench, we can call that, we can use the Gs mu b. So it's probably 4 mu b per ion. And in this case, we have a 2 mu b per vanadium. Okay, that's a simple case. But in my studies, we just put a little bit more ion in here. So nominally it would be 1.5. So actually, we can say to the Fe2 plus 1.5 minus X and Fe3 plus X. So that means that a part of the ion becomes trivalent. So where should be this trivalent ion located? You can put it in maybe in A side and maybe also in B side. But the most important is the electron configuration for the trivalent ion will be a 3d5, and only electrons based on the Hahn law will be half field and all have a parallel spin. So the total magnetic moment will be 5 mu b per ion. And the similar for the vanadium, we would be lose some vanadium occupation. So here there are some vanadium must go to the 4 plus at tetravalent. So its electron configuration will be 3d1. So we only have a 1 electron occupied at T2G orbital. So the total magnetic moment will be 1 mu b per vanadium. So the situation will become very complicated because we have 4 mu b, 2 mu b, 5 mu b, 1 mu b. And we also have different electron configuration and the unoccupied number of orbitals. So that would be case the hybrid for the charge orbital and the spin. So it will give you very complicated physical properties. Okay, so that's the basic idea for this systems. And now I am trying to introduce several important papers that related to my research. So the first one is let's study the typical ion vanadium oxide. So in the beginning, they also mentioned about very important things is crystal structure. So from the high temperature to low temperature, its crystal structure would be firstly in the cubic phase, about 138, about 138 K, and it transforms to the tetragonal phase between the 130 to 111, and then it further goes to the orthorhombic phase, and it between the 75 and 111 K. Then you go back to the tetragonal phase again at a low temperature. So this structural change will influence its magnetic property because I just mentioned about its magnetic and its crystal structure will highly correlated. So too loud, right? Okay. So as the structure, as its crystal structure in about the high temperature tetragonal phase, it forms a paramagnetism. But when we go to orthorhombic phase, there's starting some magnetic order in here, and there's a kick here, which means that we return from the orthorhombic phase to the tetragonal phase. And they also use the neutron scattering to demonstrate how the this peak change and the case the shape of the peak change in this four structure. Okay, so they also do some experiment for the thermal properties. So they also measure specific heat. So they found the first change here. There's a peak we call the TS, and the second peak TN1 and the TN2. So between the TN1, for the TS1 and TN1 and TN2, they do other different tests. They apply the magnetic field to ensure that the phase change comes from magnetic. So the first peak here, they apply the 9 Tesla. So there's no difference here. So we can should make sure that the phase change comes from the structure. But for those two peaks at low temperatures, the magnetic field will push this peak to higher temperature and become broadened. So we can make sure these two phase changes come from some magnetic ordering. So here's also some magnetic part measurement. This is the magnetization. So as you apply the magnetic field in the field cool process, you will find the magnetic moment will goes to 2.5, and they also do the hysteresis loop, and the saturation moment at 5K is about 2.15 mV per formula unit. And here they also shows there will be some magnetic correlations at about 100K when you apply the 5K Oster magnetic field. So this test just tell you that where is the phase change about the structure change, and otherwise they are coming from the magnetic ordering. Besides the test of this magnetic property, they also test another physical property in AC mode. What does it mean AC mode? They test the AC magnetic susceptibility. They also found that phase change here at around 111K. But they also do very differences. They also try to plot its dielectric constant. Typically, dielectric constant is correlated with some electric polarization, right? So as the temperature cooling down, they also found 3 phase changes in TS1, TN1, and TN2. So they just do something very differently. They try to understand if this electric property will influence by magnetic. So they go to the 5K and apply the magnetic field, and they also found the difference of the dielectric constant. They have some hysteresis loop. So let's review this compound have magneto-electricity property. So that may be used for making some enriched. Of course, the 5K is too low, right? Okay, but we can always give you a scope. Okay, so in that they just express what happened to this substance. So at a high temperature, about 138K, they are cubic phase, and they are going to the high temperature tetrahedral phase, go to the orthorhombic and the low temperature tetrahedral phase. So in this case, their magnetic property would be triangular ferrimagnetic below the 56K, and the collinear ferrimagnetic phase at the 111K, and the paramagnetic phase about 111. And what's the correlated with the structure and the magnetic property? So in the beginning, when we cool down, the first thing that we will contract due to the cooling, right? So both the pyramid, the FeO4 side, and the octahedron and the VO6 side are compressed. But when you further go to lower temperature, the FeO4 pyramid will not further compress again because they don't have free orbitals that I just mentioned in the beginning. So which one can compress more? So the octahedron side can compress more because they have 3 or 4 free orbitals. And when you go to the lowest temperature, then there would be reconfiguration try to stabilize the orbital and its spin. So we will see the FeO4 still be longer, but the FeO6 is still compressed. But this here there is some adjustment make this stable become stable, so it will give you a higher symmetry relative to the orthorhombic phase. So actually, this study would be there are some reports in 1963 about its phase with the different compositions. So they also report there were cubic phase, tetrahedral phase, two types of tetrahedral phase and orthorhombic phase. And how to prove that there is some spin and orbital interaction and stabilize this crystal structure? So they do the inelastic neutron scattering and found there to be a spin gap at 3.5 K, and this peak is 6 above the 111K. So based on these experiments, we can also study its spin gap, and we can also get the spin wave velocity from these experiments. So I will do a similar experiment later, but we show the different result. Okay, so this is my experiment. So firstly, I do X-ray diffraction in my laboratory, but you want to know the detailed structure, you need to go to the synchrotron. I think this is still in the TPS 19A, so now it shift to 9A, right? 09A, right? And of course, we just hit some stainless steel, so there's two extra ion peak. But actually, this pattern is quite good, so we can identify its compositions. We have very good fraction for the ion and the vanadium and the A side and the B side. So we know there are seven ions in the A side, but the A side have total 8 positions. And there was 1:2 ratio between the ion and the vanadium and the B side. Okay. Of course, we also confirm that by neutron scattering because the neutron did not see the vanadium. So we can first fix the composition of the ion, and we go to the synchrotron radiation. Okay. Too loud, right? Interference. For the neutron, unfortunately, the neutron also detect the magnetic structure, and I will tell you the magnetic ordinate is still hold until the 475K. So I will go to very high temperature, identify the number of the ions in this compound, and we go to the room temperature and fix the ion number and refine the vanadium in the synchrotron radiation. Okay, and we also tested the specific heat, and this is the result. So we found we also applied the magnetic field, but we found 3 peaks here at 220, 187, and 157. But there's nothing changed when we apply magnetic field. That means that there's some variation of the structure that is irrelevant to the magnetic ordering. And we also did the magnetic susceptibility measurements. So we have the field pool and the zero field pool process. So as you can see, when we apply the 100 Oersted magnetic field, the efficiency and the ZFG curve depart at about 400K, and if we have 500 Oersted magnetic field, it departs at around 200K. So that means the magnetic correlation, I will say the correlation would be higher than the 400. But due to the instrument limited, we cannot get more information about the 400K. And we also did some the H magnetic susceptibility measurements, and we used a different frequency. That's just to probe if there is some magnetic cluster inside the system. So we found some dependence that when we apply the higher frequencies, the peak intensity is slightly suppressed. That means we have some magnetic correlations, not so long range, but it will be influenced by the applying the frequencies. And this is the hysteresis loop test. In this case, we go to the base temperature 2K, try to fit with the Brownian function to know the mu-z, which means the saturation magnetic moment per formula unit. So here we fit the equation with the Brownian functions. We got the total magnetic moment is equal to 2.26 mu-b per formula unit, which is very close to the report, the previous report. And we found there's some cohesivity at a low temperature, but at a high temperature, then you can see the shape of the hysteresis tell you that they already have some magnetic correlation, so that look like a linear. So there's some saturation moment you can align by the applying magnetic field. Okay, so before we doing some for more analysis, we have some neutron powder diffractions. Unfortunately, we don't have another bin time, so you will see the pattern will be a little bit noisy. But at least we can tell the difference between these temperatures, right? So, okay. So if you compare, you take a look at these patterns very carefully, you will find there's a peak. There are two peaks and variation of this peak intensity. So we can do some structural refinements. And in this case, the red class is the observed pattern, and the red curve is the fitted pattern. And we use the FT3, cubic FT minus 3M nuclear structure to refine its nuclear structure, and the magnetic phase with the FT minus 3M plot to fit its pattern. So we got its magnetic structure. It looks like this, which is very similar to those we call at a very low temperature. But there's still some difference because I only put the magnetic ion in the A side, but they just refer them with both A side and B side contains magnetic moment. And then we just fit this magnetic moment at the various temperatures. So okay, I did not mention one thing. So you can see here, we only have a limited time, so we only collect 3.3K to 150K, and there is some space between here, so the next temperature is 300K. So when we refine these patterns, you will find, unfortunately, there is a gap here, and we have no idea what happened here. So above 150K, we know the magnetic moment is roughly 1.5 mu-v, and above 300K, we know it's close to the 0.8, and we don't know anything. So of course, we can get the lattice constant for this red solid circle here and here. So we need some, okay, we need some more information. So I go to the synchrotron X-ray and at these points, but we don't see any structure change. So that means we need to go back to do some neutron scattering and figure out what happened in the magnetic structure, not in the nuclear structure. Okay, so this is okay. That's two slides. So let's bounce. I go to the end. So I go to the SIGCA to detect it, to do the ADS neutron scattering, and to figure out if there is any spin gap here. So the origin of the spin gap is if there are some spin orbital interaction, then there would be created a spin gap to lower the energy for as they form the crystal structure. So they will let the orthodynamic phase becomes a tetragonal phase for previous papers report. But in my case, we found here the spin many gaps at the different Q. So I use this different Q because I only have powder sample. Typically, if you go to the Zika, you need a single crystal sample. So I write the Q number instead to the Miller index. This is because there are many, maybe at least 2 Miller index have same Q value. So I just write this one. But actually, we can. In the beginning of my opinion, that we want to detect the 1-1 peak. If there's nothing here, that means we don't have spin orbital interaction. Okay, but we found that there is excitation here, so the energy is roughly at 6.8 MeV. No matter in the 1.31 Q and 1.31 angstrom. Or 1.57, 1.82, they are all excitation. So that means there's a strong spin orbital interaction, and the temperature range included from 1.5K to 300K. So this interaction is very strong, even it can survive at the room temperature. So this is the fitting value of this gap. So we also missing something here. Due to the limited time, we already spent 8 days there, but we still, it's still not enough. Okay, but we did see some integrity that it decreased, a little bit decrease at a high temperature. We will not know that where is the tail. Okay, so this is my conclusion. Okay, the crystal structure of the FBO very speed cubic FD-3M with the temperature range of 1.5K to the 475K. And the magnetic correlation commences at the temperature exceeding 475K. We don't know where is the limit of this magnetic correlation. And below the 150K and above 300K, so you know there's a gap that we missed some experiment. And that sample exhibit a magnetic structure characterized by the space group FD-3M prime. And there's an energy gap indeed by spin orbital coupling quantified at 6.8 MeV and have been observed consistently between 1.5K and 300K. So maybe that will be exist at a higher temperature, but we have no idea. Okay. So that reminds us on unsolved complexity. Consider the interplay among the charge orbital and the spin interaction in this system. So actually, we study a system is not quite new, but there are no other group report something like this. Especially they have a very strong spin orbital interactions. How come? So we need to figure out this in the near future. Okay. So I would like to thank a very persons, Jingwei Wang, he helped me to the neutron powder depression, and Jianlong Huang helped the heat specificity and magnetic sensitivity measurement, and Chen Wei helped for the magnetization and distortion loop, and Tong Longxiang for the experience assistance, and the Yano, Dr. Shishong Yano helped for the ES neutron scattering. And my group, part of the students come from the Zhongyang University, helped me to do the neutron scattering. Of course, we must thank the NSRC for the time slot and the travel expenses. Of course, we cannot forget the NSDC. So please take a picture here to prove that I did make an acknowledgement for those institute. Okay, thank you for your attention.
Okay, thank you very much for Professor Yang. Very nice talk. Yeah, maybe you know Professor Yang is the former president of the Taiwan Neutron Science Society. Yeah, so yeah, he's real neutron guy. Okay, so now let's open the question from our audience. Yeah, please. Yeah, you want? Yeah, lady first. Okay, yeah.
Thanks for your talk, and I just want to ask a very easy question. The question that since you say that the time is limited, right?
Right.
So for your experience, and I'm really interested about. So how long do you expect that you can fully finish your experience?
Oh, actually,
So just
which
a
one
little
you
bit
mean
curious. Maybe this one or
this one, okay.
or the temperature loss. I think the
No.
gap you see.
Actually, I think if I have the double of time, means that we have a 16 days, then maybe I can complete all the experience I need. But the 16 day, I think is not possible for the typical proposal, so we will need to travel twice. Or actually, now we know the SICA can do experience remotely. If we don't have a lot of the travel expenses, maybe we can ask the instrument side to help us to finish this experiment if they have some free time. Okay, we can say that officially, right? Okay.
Okay, maybe tomorrow, the working day, we will talk, discuss with Sijun how to satisfy the requirement of the user, okay?
Actually, this time we got a grant for the two person, but I take the 4 students here, so we just share the travel expenses. Because I want to promote this, the neutral technology to students, and I think the NSRC support the budget, then how to use that we can decide ourselves.
I see. Yeah, maybe we will do our best for how to increase the possibility of the travel budget. Okay.
But I think one more thing is that most of this experience can do remotely, but you need to have a good conversation with the instrument scientists. So maybe that will encourage more people if they got the permission of the experiments. They may not, but I think that at least one time they will do outside.
Yeah, very good idea. Okay, thank you. Yeah, so.
Okay. How do you know that the inertial scale peak is come from spin over the equation coupling?
Okay, that's a very, very good question.
Something else, right?
Right. Okay. Actually, in these systems, we need to some proof with some structural refinement and check if there is some electron configuration and the orbital have correlation. But unfortunately, we don't have such kind of information at noise temperature because we got the very noise neutral patterns, and unfortunately, we cannot get the 1.5K from NSRC because NSRC has a very high resolution. So we can refine and get the bond length and bond angle between the atoms and show you if there are some orbital ordering here and a combination with the spin ordering. And we can also do one experiment that if we got the 1.5K NSRC, then we apply magnetic field to influence this coupling trace, then we will see if this is coming from a spin orbital direction. But now I just refer from the paper, so if we can get more time for the neutron, or if the NSRC purchase a new low temperature equipment in 009A, right? TPS 009 or 098, then maybe I can prove that. Sorry.
Well, division head, do you want to comment on it?
Thank you. No, actually, I don't have any comment on that. But I'm actually curious about that because our colleague is developing magnetic scattering, X-ray magnetic scattering. Can that help with your topic?
Yeah, perhaps. You mean the RIX or?
No, I think in 098 they are doing magnetic scattering, starting to use that, and so.
Yeah, perhaps. Yeah, calculate the temps, but the question is the sample environment.
Yeah, the temperature. Okay, that maybe we can discuss that.
Because if you want to develop anything about the magnetic properties, you must take care about the sample environment. Most of this technology will be at a low temperature. So even you need some dilution facility. I'm not sure if there's some people study some like spin ice or some quantum computing materials that will go to mini K. But I know it's very expensive and very hard to operate that. Yeah, that's only my suggestion.
Okay.
I do not go to the such low temperature. If we have liquid helium, I would be very happy for that.
Supposedly the low temperature being TPS 09 being like no problem. So
for liquid helium,
supposedly
I know in the TLS there's a closed cycle refrigerator that we can go to probably 15K, but I know this equipment is broken. So and now I know if we want to do some temperature variation experiment to 10K, it is not possible in the NSRC now. That's what I know.
Okay, yeah, thank you then. I have more missions to discuss with our colleagues. Yeah, thank you.
Okay, due to time limit, let's Professor Yang again. Thank you. Okay, the next speaker will be